Hello everyone, my name is Zilu. This is the class project for ECE 6258 Digital Image Processing. Our project topic is recognitions in images, improving the result from challenging unreal and real environments for traffic sign recognition paper. First of all, I would like to introduce the background of this project. The traffic signs are an important part of the road infrastructure. They provide road users with some key information and require drivers to adjust their driving behavior in time to ensure compliance with the road safety regulation. If there is no traffic signs, more accidents may occur. Hence, a serious and immediate action need to be taken. There are a lot of difficulties present to the driver that hinder their ability to properly see the traffic sign. Some of those difficulties are lightning conditions and weathering conditions and etc. Hence, it is necessary to let the computer to learn and recognize the most critical features of those traffic signs, then present those information to the drivers. That is potentially a way to decrease the number of traffic accidents. So the previous team was investigate the performance of traffic sign recognition algorithm under challenging conditions. They've split the dataset into 5 challenging conditions and use 7 different recognition methods, including intensity softmax, intensity support vector mechanics, RGB softmax, RGB SVM, RGB convolutional neural network, HOG softmax, and HOG SVM. With all those methods being used, they proved that the challenging conditions will decrease the performance of baseline method significantly. As a result, they found out that using diverse challenge conditions data could enhance the recognition performance in the real-world scenario. The GitHub repository within the paper contains the code to reproduce the benchmarking result for RGB convolutional neural network. Without any pre-processing method done, our team has decided to first reproduce the result using the existing code to prove that the conclusion we got is consistent with the paper. On the figure left, here is the result we have. Notice that there are small errors between the result we have and the paper. For example, if you look at the Gaussian blur module for challenge level 2 and challenge level 3, as the result we have, for challenge level 2, the error and the accuracy is around 60 something, and the accuracy for challenge level 3 is around 50. However, in the paper result, their accuracy for challenge level 2 is around 70. For challenge level 3, it's around 60. We think the error might be because we use different number of epochs and learning rate to train the network. These small differences do not have much impact on the network's performance. After we produced the training result, our team thought one important issue that dragged the accuracy down is the image quality. From there, we decided to do the pre-trained image processing first. The main purpose of it is to improve the visual quality of the image. So the first technique we use is called the histogram equalization. The goal of histogram equalization is to nonlinearly stretch the image to enhance the dynamic range of the pixel value so that the image can use the entire color level. As you can see from the left figure, this is a histogram of original darkened image in challenge level 3 dataset. You can see all the pixel intensities are concentrated in the 0 to around 52 level. So the histogram is pretty unbalanced. But after the algorithm we apply on the histogram equalization, you can see the pixel level is sort of distributed on the entire color level. However, we decide not to apply the histogram equalization directly on the RGB color plane. Instead, we transform the RGB plane to another color space called YUV color space because it contains luminance or brightness information. The YUV color space is to separate luma and chroma. The Y means brightness, which is gray level. The U represents the difference between the blue channel and the brightness, and the V represents the difference between the red channel and the brightness. So with the brightness information, we can apply the histogram equalization only on the Y plane. And after all that, we merge those 3 new planes into a new picture and then transfer this picture to RGB color space. So we are able to apply this method to both 5 explosion image datasets and 5 darkening image datasets. As we are not expected, using this method will result in some loss of details in a certain region. As you can see from the exposure image we generate here, there is some strange pixel blocks right here in the middle of this picture. Those small strange pixel blocks extremely affect the training performance of the RGB CNN network, as you can see from the result we generate. Moving on to shadow removal. The shadow datasets contain images with artificial shadows. Those shadows are a factor that prevent the detection accuracy. Therefore, our team tried to discover a way to balance those shadows out. We first input a set of images and split them into 3 different planes, R, G, and B. Then we delete each plane and then apply a medium blur filter into each plane. This is because we want to get rid of any foreground information. Thus, any leftover should be an image containing only background. After all that, we calculate the difference between the original image and the background image in each plane. Now, the shadow information should be gone, and we normalize the result image and merge those 3 planes back together to receive a new RGB image. However, the result looks not really good. As you can see, this is the original image from a challenge level 5 of the shadow image. And this one is using the algorithm to remove all the shadows. Even though it balanced out the shadow region and the non-shadow region, it lost a lot of color information, as you can see from here. And overall, it also have a crack line on the center. So add those bad factors together, the training result for the shadow removal image has actually lower accuracy than the corresponding original image datasets. The third image dataset we process is haze image dataset. The contrast for haze images is extremely low compared to the original challenge-free image. With the increase in challenge levels, the contrast even decrease more. But instead of doing a normal histogram equalization, we want to try adaptive histogram equalization. The image is divided to small blocks called tails. Then each of those blocks are histogram equalized as usual. There is a base class for this technique in OpenCV, so we are able to using that method and apply the algorithm we have into the L plane with the fixed clip limit and default grid stats. Here is the result we generate. As you can see, the contrast increased significantly. However, the image is now smoother than before. You can see the sharp edge and the small little blocks on this image, and those small blocks and factors actually affect the training result. As you can see, the challenge 5 is significantly bad, so the accuracy level it dropped very high compared to the non-processed haze image. While we are processing 3 datasets mentioned above, we realize that there is one important artifact in image capturing which is not mentioned in the dataset. It's the motion blur artifact. When a camera captures an image, it does not only show a single instant image. Due to the technical limits, the image shows scene over a small period of time. If we treat the vehicle as a reference that does not move, then any traffic sign is moving in the relative direction of the camera. Thus, the result image will look like very blurred or shaken. So we applied motion blur based on the image size and the motion angle. As you can see in the middle, this is the blurred image. We learned from the class that Wiener filter not only can reduce the image noise, but also can eliminate image blur caused by motion and other factors. So we are able to transfer the image into spatial domain and apply Wiener filter on it. So here, the CNN performance for motion blurred image is around 40 accuracy. But after the filter by Wiener filter, it improved significantly to around 70% accuracy. There are a lot of future work that could be done in this field. Remember, 2 of the image datasets we processed does not increase the training accuracy. Even though it looks like a lot more better in terms of contrast, they introduce another defect that confuses the neural network. Therefore, the number 1 priority should be refine each of the pre-processing algorithm. Unfortunately, or team is unable to test the softmax and intensity-based method. So if we have extra time, we definitely want to test each of them. Personally, this is the second time I took digital image processing class. I took another class at different institution, so I can say I can directly compare this class together. So I want to use this opportunity to thank Dr. Alrajib. It's not easy to deliver the class online, especially with those COVID situation. But I feel like I learned so much. I learned from image representations to image transforms, from image codings to image enhancement. Before I took this class, I don't even know how broad the image processing field could be. And after this class, I feel like the image processing is so much fun. I would 100% recommend this class to my friends. It's not only focused on the basic of DIP topics, but also show you the future research directions. It is a fantastic course that pushes you out of your comfort zone. That's it for the project. Thank you for watching. If you have any questions, please email me.